Hey folks, this is Cap Jones here to talk to you about how we might actually return from the HALT instruction on the LC3. The textbook has kind of teased this almost the entire way, and although it never quite explains how to do that, based on I think some understanding I've got of microcontrollers, there's a possible solution that I want to share with you today. So our objective is going to be to describe that circuitry that potentially allows the LC3 to be restarted after a HALT instruction. Let's get started. Okay, so recall that the machine status register has the clock enabled bit, and as long as that bit's a 1, then the clock signal that is generated somewhere gets sent to our LC3, and that's what sort of runs the whole processor. And when we issue the HALT instruction, we clear this bit, that goes to 0, that stops the clock from going to the processor and effectively halts the processor. And so it would seem all hope is lost, since running any sort of instruction to try to set that bit involves the clock, unless we remember that this register is very likely built out of some type of D flip-flop. And if you recall from EE360, our D flip-flops have asynchronous signals. We can set this bit, the clock enabled bit, without needing a clock signal, using that asynchronous set. So you can imagine that we're going to wire that to our interrupt signal. And so after we issue our HALT instruction and this bit is clear, the LC3 doesn't do anything else until an interrupt is generated that would need servicing. That interrupt signal, if it goes to the asynchronous set on the clock enabled bit, can turn that back into a 1, which allows the clock to go back to the LC3, and now we can sort of restart our processor. We can finish running the HALT the HALT trap routine and then continue on with our interrupt. So what this the one kind of catch is that we have to be careful that the generating the interrupt signal either doesn't require the clock signal, or we set up our processor so that the clock enabled bit turns off, like a main clock to the processor, but there maybe is a separate clock signal that goes to the peripherals that allows the interrupt signals to be generated. So by that I mean if you were to look at the hardware for generating these interrupt signals, it might very well be that these bits here in the status register are clock signals. They're set by a register, and so if the interrupt signal is dependent on a clock, that can't be the same clock that we're turning off here to halt the processor. So as long as one of these two conditions are true, then we can use the asynchronous set signal on the clock enabled bit to restart the processor. And so hopefully now it kind of starts to make sense that when we are in our HALT service routine, why we might have these instructions that are at the end of the routine here, as if this routine would ever terminate, because after we halt, then there's a possibility of an interrupt sort of awakening or restarting the processor, so it is. So that's the purpose of these instructions down here. It is it's in this store instruction where we are sort of storing, clearing that bit in the machine MSR. Or I got MSR. This is MCR, the machine status register, or whatever MCR is. And it is right in this bubble here in the execution of that store immediate or store indirect instruction. We'll take a look. This is the kind of the flow chart for our processor, which we'll look at in the next unit. But as we're processing this store indirect, right at that moment where we load that register with R0 to clear the clock enable, is the moment when the clock to the processor is turned off. And so if we set up our interrupt signal this way and reawaken the processor, then once the processor, that clock's turned back on, the very next thing that happens is the processor will start executing the next instruction, which down here, terminates the trap service routine to halt the processor. So the last thing I want to show you is how this actually kind of plays out in real life. So I'm going to pull up, this is the data sheet for the ATmega 168. And this is the exact microcontroller that is on the Arduino Uno microcontroller board. So if you're familiar with the concept of an Arduino, and how you can use that to sort of write programs and turn lights on and off and stuff. Well, this is the microcontroller that powers it, or at least one of those boards. And if we go to this section here on sleep modes, what you'll see down here are that we've got a couple of clocks that we can control on the Arduino. The CPU is one clock here. We've got a couple other clocks that go to our inputs and outputs and some other stuff. And we have a variety of sleep modes. So on the LC3, we effectively have either asleep or awake. On the Arduino, we have various levels of idle and power down and power save that sort of gradually turn stuff off in the microcontroller, and that allows certain things to sort of reawaken the processor at some time in the future. And for microcontrollers, this is very important because very frequently microcontrollers are used in scenarios where we need to use the least amount of power possible. We're running off of a battery for weeks or months or years even. And so I'll skip a little forward in the data sheet to this section here on the DC characteristics to show you the current that gets drawn in the Arduino in each of these power down modes to sort of show you how significant this is. So this line of here is telling you that basically when the Arduino is running its programs, it's pulling somewhere between 7 and 9 milliamps of current. And if we go all the way down to our lowest sort of sleep mode, our lowest power down mode, you can see down here that instead of drawing 9 milliamps, I'm drawing 2 microamps. So this is a factor of at least 1,000 times better than when my Arduino is just sort of running away on whatever program it's doing. And so when that difference of 1,000, that's you could sort of turn that around and say, okay, well, if my Arduino could run fully on a battery for a day, if I'm able to power that down all the way for a significant period of time, I could maybe run that for not just a day, but 1,000 days, which is, over 3 years or about 3 years, right? So, so for microcontrollers, being able to go down to these various sleep modes can really allow for some significant power savings that are able to extend the battery life on these things very, very significantly. Okay, so to recap, today we talked about how it is that our processor might return from the halt instruction when all hope seems lost. And the trick really just came around realizing that this register, the clock enabled bit on the machine register, has potentially an asynchronous set signal. And if we tie that signal to our interrupts, well, now we have a perfect avenue of turning this clock back on after we've turned it off. Which would happen if there were some sort of hardware device that required some servicing, so in that manner, after we execute this store instruction in the halt service routine, it makes sense that we might be able to come back and execute the rest of this service routine and continue processing if there was an interrupt that sort of forced the clock enable bit back high. And then we also looked at the datasheet for the Arduino. We identified that there are also a couple of different save modes, power down modes on the Arduino, and that can potentially make a difference in power consumption of a factor of 1,000, which is really significant in being able to allow that Arduino to potentially run on a battery, or allow our processor to run on a battery for a very long period of time. All right, folks, that's all I got. I'll see you next time.